Okay, so this is a video about forces part 2. These are the level 2 questions. So the first one asks about the equation that links force and work. So work done, remember from the last one, is equal to the force times the distance. Okay, so we're going to use this equation. The distance travelled is 200 meters, as we can see in this equation, and the force is equal to the weight of both Greg and Jill. So we've got a weight of 700 and 500 together. So if we add those two together, we will get 1200 newtons, and we're going to multiply that by the distance travelled, which is 200 meters. That will give us a work done, remember, which is in joules, and that's 240,000 joules. Okay, the next question. The chair takes 5 minutes to move from the bottom to the top of the ski slope. So we're calculating the power. So remember, power is equal to energy divided by time. We've just worked out the energy, which is the work done. So we're going to do 240,000 and we're going to divide that by the time taken. Now this has to be in seconds. So 5 times 60, okay, equals 300 seconds. So we'll get rid of that now. We know 240,000 divided by 300, and that's going to give us our answer, which we can write up here, is 800 watts. Remember, power is measured in watts, and that's a capital W. Okay, the chairlift is driven by an electric motor. Why would the power output of the electric motor need to be larger than your answer to part B? Well, if you think about it, the chairlift carries 2 skiers, but all we've had is the weight of the 2 skiers. There's been no description of the weight of the actual chairlift, so doesn't include weight of chairlift. Okay. So the next question, when the ski lift is working, some kind of energy is supplied to the motor. So for a motor to spin, we need to have electrical energy. Remember, electricity goes into the motor and that causes a magnetic field causing the motor to spin around. When it spins, the energy is transferred as gravitational potential energy. Okay, the next question. So we're going to fill in this table. So force is in newtons, which is a capital. Distance is in meters, which is lowercase. And work done is in joules, which is a capital J. Okay, the next question. The diagram shows a builder using a plank to help load the rubble into a skip. So the builder uses a force of 220 newtons. Okay, so in this particular question, because it's going up a ramp, the force of both the work done against gravity and the work done against friction are taken into this account. So that is the work done against gravity and friction. So the work done is equal to the force, which is both of them, times by the distance moved, and the distance is going to be 220 newtons, so that's 0, and we're going to times that by the distance that they've moved, which is 2.6. That will give us 572 joules. Okay, carrying on. Okay, so on this question, a student investigated how the force needed to pull up a brick up a slope at a steady speed depends on the angle. So the first thing they want you to do is to draw a line of best fit for these points. So, because we don't really know what's going on before this, I'm going to start from the X and we're going to draw a nice curve through those points like so. Okay, how does the force used to pull the brick up the slope changes the angle of the slope increases? So you can clearly see as the angle increases, the force also increases. So when you are describing a graph, you always state how changing the independent variable, the angle, affects the dependent variable. So as we increase angle, we increase force. Okay? Right, consider the results from this experiment. Should the student recommend that the builder use a long plank or a short plank to help load the skip? Well, we know that if the angle is less, then the force is going to be less. So if we have a skip here and we choose to use a short one, then the angle is going to be great. If we use a really long plank, then the angle is going to be lower. This angle is going to be less than this angle, so therefore using a long plank is going to mean a shallower angle, and if we have a shallower angle, we will need less force. Okay, right, a student suspended a spring from a laboratory stand and then hung a weight from the spring. Okay, so we know this experiment is related to Hooke's law. Measure the extension of the spring. So we're going to draw a line across here. Now when you do this, make sure you always use a ruler. It's quite hard to do with this. Okay, so we know that's from the bottom to there, so then we need to do it from the bottom to there. And you can see that's gone up 1 centimetre, not quite 1.5, probably 1.3. So 1.3 centimetres is going to give you 13 millimetres. Okay, before taking any measurements, the student adjusted the ruler to make it vertical. Explain why adjusting the ruler was important. Okay, so we just need to know that the extension is measured correctly. So extension is measured correctly. Therefore, there is no error in the measurements. Always try and talk about the error. Okay, clearly, if the ruler's at a slant, then the measurement is incorrect. The ruler needs to be exactly straight. Okay, so moving on, the student measured the extension of the spring using a range of weights. What range of weights did the student use? Well, he used a 1 and right through to 6, so 1 Newton to 6 newtons. Why does the plotted data in figure 3 support the student's prediction? Okay, so if we go back, we can see that the student, before starting the experiment, the student wrote the following prediction. The extension of the spring will be directly proportional to the weight hanging from the spring. So his prediction was that this is directly proportional. Now we know directly proportional means a straight line that goes through the origin. So straight line through the origin. And by through the origin, I mean at 0, 0 on the graph. Okay, so that is what directly proportional means. A straight line graph that starts at 0, 0. So we write through the origin. Describe one technique that could be used to improve the accuracy of the measurements taken. Okay, so imagine that this is the spring and we have a ruler. Okay, so maybe on this we could put some kind of needle to measure it. So if this would be the spring, on the bottom of the loop we could have some kind of needle pointer, and then when that goes to the ruler it would give you an exact measurement. Okay, so a horizontal needle to accurately measure extension. Okay, and the reason for this is because it goes across the scale. Okay, if this is the scale on the ruler, you can see that that would be going across the scale, so we get this exact point instead of having to guess where exactly that is on the ruler. Okay, the next question. At the end of the investigations, all the weights were removed from the spring. What can you conclude from figure 4 about the deformation of the spring? Now remember, when we get this curve, this means it has gone past its elastic limit. So it will have deformed inelastically. So it would be inelastically deformed. That means it will not return to its original shape. Okay, and we know that because at this point here it is no longer directly proportional. Okay, So the spring has passed elastic limit. And remember, this point here is going to be your this point here is your elastic limit, or the limit of proportionality. Remember, you can use both terms. Okay, the next question is about pogo stick. So the child and pogo stick are not moving. The downward force of the child on the spring is equal to the upward force of the spring on the child. So what type of law is this referring to? Well, this is an example of Newton's third law because this is an equal and opposite force, so we will tick that one. Okay, the compressed spring stores elastic potential energy, so that's going to go there. Okay, so remember, when you stretch or compress a spring, you are storing elastic potential energy. Okay, write down the equation, which is gravitational field strength, mass and weight. So remember, our equation is that weight is equal to mass times gravity. Calculate the mass of the child. Well, we need to rearrange this equation, so we know if W is equal to M times G, then if I need to move G, I can divide by G on both sides. G will cancel out, so therefore mass is equal to weight divided by G. That should be a G, by the way. Okay, so we can now use that equation. It's given as 9.8. It will always give you the gravitational field strength. So it could be 10, but in this particular equation, it's 9.8. So we need to know what the weight is. So if we go back to the previous part of the question, it says the child weighs 343 newtons. So 343 newtons divided by 9.8, and that's in newtons per kilogram. Okay, so we can cancel out the newtons, and that gives us our kilograms, and that answer will give us 35. So 343 divided by 9.8 will give us 35 kilograms. Okay, so the weight of the child causes the spring to compress elastically from a length of 30 centimeters to a new length of 23 centimeters. Write down the equation which links compression, force and spring constant. So we know force is equal to the spring constant times the extension. Calculate the spring constant, so we need to rearrange this. So K is equal to force divided by E. Okay, so what is our force? Well, we've got that from this equation, so that is 343, and we're going to divide that by the distance, which is an extension, and that is from 30 to 23. So that's a change of 7 centimeters. Now remember, 7 centimeters isn't in meters, so we need to divide that number by 100, and that will get us 0.07 meters. So we're going to divide that by 0.07 meters, and that will give us 4,900. Okay, make sure your answer is in the appropriate units. Right, the next question. So it says the diagram below shows different stages in a bungee jump. Forces A, B and C are forces acting on the jumper at each stage. So here you can see the jumper is accelerating. Why is he accelerating? Because there's only one force, so the resultant force is down, and if there is a resultant force, the object always accelerates. Here they are moving down with a smaller acceleration because the resultant force is smaller. There's a force pushing up, there's a force pulling down, but force A has to still be bigger than force B because there's still a small acceleration. Remember, you get acceleration in the direction of the resultant force. Here, there is a slowing down, so there's a deceleration. To cause deceleration, force C would have to be greater than force A. So the first thing is we're going to label the forces. So the force pulling down is going to be weight. Okay, so force A is weight. Force B is not asked in the question, but we're going to write it anyway in case it comes up. So this is going to be tension. So you get tension in the cord or in a rope. So tension is this force pushing back up again. The motion of the jumper is shown in the diagrams. By comparing forces A, B and C, state how the motion is caused in the diagram. Okay, so force A is the only force. So if force A is the only force, we're going to get a resultant force, and that is going to be equal to force A. because it's the only force, and therefore we get acceleration. Remember, you always get acceleration in the direction of the resultant force. Okay, for diagram Y, force A is greater than force B. How do we know this? Well, the object is still accelerating, so this force has to be bigger than this one for the object or person to accelerate. Okay, so we know that because there is a small acceleration. It says small acceleration, so we know that force A has to be greater than force B. In the last one, diagram Z, you can see that the person is slowing their acceleration. They're moving down. So a slowing acceleration would mean a deceleration. Okay, so if the acceleration is slowing, then force C has to be greater than force A. So force C is greater than A. And if force C is greater than A, you get deceleration. Okay, so we're going to plot these results. So the first one is 120, so we're going to go across from here and up from there. Be very precise when you do this. I'm going to put some dots on there, but make sure whatever you're using, and you should really be using a pencil and a ruler, is very clear to the examiner. The next one is 224. You know, up from 200 and 224, which is about there. 400 we go to 32, which is roughly speaking around there. Then at 600 is 40, which is there, and then the last one at 800 is at 48, which is there. Okay, and if you do that, just put 640 again, then you should get a straight line. Okay, dependent on the accuracy which you put this. It says use the graph to find the length of the cord before it was stretched, so that means we would go straight back. Now remember, if this is a straight line, it's direct. We've got a directly proportional, so it should go to roughly around there, and this length is roughly 16 meters. Okay, so by using our graph, if you use a ruler and you do it accurately, you'll get around 16 meters. Okay, the next question. The extension of the spring is the distance between the positions labelled. Well, for this one, you can clearly see that this is where it starts, and this is where the hook has gone down to there. So it's this difference here, which is between B and C. So that's the bottom of the spring. So you're looking for the bottom of the spring, and then you're looking for where the bottom of the spring goes to. So it's gone from B to C. What form of energy is stored? Well, this is elastic potential energy. Okay, right, the error made in this particular question is that they have clearly plotted the length of the spring. They have plotted the length, not the extension, because the extension would always start at 0 if there is no force. So at 0 newtons you will have no extension. So the reason for this is the extension starts at 50 millimeters. If they'd have done it correctly, at 0 newtons, the extension should always start at 0 millimeters. There should be no extension when there is no force on the spring. Okay, the next question is about the limit of proportionality, and that you can clearly see is where this curve starts, which is roughly about here. Okay, so make sure you do this accurately. On your exam, the graph paper will be much clearer, it'll be bigger and easier to spot. So if we go up from that point, you can see that's roughly about 5.4 newtons. Okay, so 5.4 newtons. And why did we choose this point? Because this is where the graph starts to curve. So the graph starts to curve. And what does that mean? It has reached the limit of proportionality. Okay, limit of proportionality, or the elastic limit. Either one mean the same thing. Okay, so the next question, when the student hangs a stone from this spring, its extension is 72 millimeters. Again, this has to be in meters, so be very careful. So we're after the force, that's equal to KE. The spring constant is 25, which is K, and then we're going to multiply that by this in meters. So remember, 72, there are 1,000 millimeters in a meter, so we're going to divide that by 1,000, and that will give us 0.072. So we're going to times that by 0.072, and that will give us 1.8 newtons. Okay. Right, here are all the answers. So I'm just going to play these through slowly in case you use this and you just did the exam questions by yourself.